हाँ जी
ऐसे मैं लोड वेरी अच्छे से कर पा रहा था, तो डिफलेक्ट कम आती है उस बीम में। तो कन्वेंशन के हिसाब से उसको 1.1
can we have a beam like this where the depth is less and width is more? Why can't we have a beam like this? Why do we have a beam like this in this fashion? Deflection is one thing, right?
Flexural rigidity, sir. Flexural.
What was the purpose of a beam? The purpose of beam was to reduce deflections. That was the main purpose. Apart from it is transmitting load, that every member is transmitting load. So somebody also told that it's offering stability at the same time, and that also. But the main thing is it's preventing deflection. Now this beam will have more chances of deflecting if the width is more than the depth. When the depth is more, the moment of inertia is about this axis, x-axis. This, where will the moment of inertia about x-axis will be more? In this case or in this case? In this case, because then it will be BdQ by 12 is the moment of inertia. And this, what does moment of inertia have to do? Stiffness. What is stiffness? It's moment of inertia into the lever around there, isn't it? So you are providing when moment of inertia is more, or you can say then I is the moment of inertia divided by the L, the length offers you the stiffness. Now where the moment of inertia will be more, stiffness will be more. Stiffness is I by L. So you will have a stiffer section when D is more. There is cube associated with this. With D. With B, it's just linear there. 1 times power. D has got 3 times power there. So D, increasing D will increase the moment of inertia. That will increase the stiffness of the section. So when you are having a stiffer section, the deflection is less. That's the reason we increase D greater than we are increasing B. So now why can't we keep on increasing? 1.5 times, 2 times D. If I take 3 times D, the section would look like this. 2 times D, the section would look like this. 1 times D, the section would look like this. Now 3 times D, 4 times D, why don't we take that? Then it no longer becomes a beam, it becomes a ball. It's acting like a ball then. What is also happening with deeper sections? Then the loads start to attract in this direction rather than in this direction. When you will have like this section, there are more chances of it buckling like a column. So it no longer becomes a beam. Under lateral load, it behaves like a wall or like a column. So beam has got a classification that it's a beam once it's between this range. And this is from convention again. This is from convention again. Now, the clause that I mentioned, 23.2, control or deflection, इसमें क्या लिखा है? The deflection of a structure or a part thereof shall not adversely affect the appearance or efficiency of the structure or finish or partition. The deflection shall generally be limited to following. Number 1, deflection should be limited to following. Number 1, final deflection due to all loads, including the effect of temperature, creep, shrinkage, and measured from the as-cast level of the supports of floors, roofs, and other horizontal members should not normally exceed span by 250. The amount of deflection should be span by 250 less or equal to of this. Now span किसे कहेंगे हम? You have a beam. It has got support at ends. This support is never a point. It's always like this. So if you take from this point, the center of the support, to the center of the other support, this is effective span. And if you are taking from the edge, sorry, not from there, from here till here, the center of the inner face of the support, then it's clear span. Then it's clear span. Now, when it says span by 250, it probably is saying effective span or clear span. You are not sure here. Or should not. What is it saying? And others shall not normally exceed span by 250. Here it's saying span length, but if you check the figure, if the figure is it's talking about clear span. This is clear span, not effective. You are not getting that probably from the code, but what I know is that this is clear span. Then the deflection including the effects of temperature, second one, B, temperature, shrinkage, after erection of partitions and application of finishes should not normally exceed span by 350 or 20 mm. So the final deflection is the first one due to all loads, including the effects of as the cast level of the supports of floors, roofs and other horizontal members should not normally exceed. The deflection including the effects of temperature, creep, shrinkage after the erection of partition and the application of finishes should not normally exceed span. Now here is for the degrees when you are putting in the partition as well somewhere. Below the beam you might have a partition wall somewhere. After you have put this, then it should not exceed span by 350. When there is no partition, it's 250. Now again this is clear span by 350. Now this is in mm. This is in mm. Now if you have a span of a beam, कितना होता है span of a beam normally कितना होता है? 10 मीटर. 10 मीटर की बीम आपने देखी है 30 फुट लंबी देखी है. What is the range of span of beam? कितना होता है range of span of beam? कितना होगा ये कमरा कितना है? कितना है? कितने फीट?
16/25.
हाँ?
16/25.
16/25.
feet sir.
मेजर करो. ये 1 मीटर है, ये 2, ये 3 है, तो there it's 6 meters. This is 6 meters around. That's how you measure by stretching your legs. This is rough measurement. So 6 meter, that's around 19-20 feet around in this direction, and you have more in this direction around 30-35. So you can get, do you put the beam in this direction or in this direction here? This direction, 6 meters. If you put the beam in this direction, do you think the beam, just by visualizing, can you put the beam, this is 10 meter in this direction. 10 meter, you can put a single beam in this direction. You will always have a connecting beam like this, then in the other direction. So the span is actually half there, 5. So we usually have, in normal circumstances, 4 to 6 meter की beam हम provide करते हैं. Now this is 4, but this is not. You can provide a 10 meter beam, you can provide 20 meter beam. ये restricted नहीं है. लेकिन जितना आपका span बढ़ता जाएगा ना, span is increasing, the amount of deflection is increasing. The amount of deflection, उससे क्या होता है? You have to provide deeper beam there. Greater the span now, you have to then provide deeper beam. The vertical deflection limit, which is given next, may generally be assumed to be satisfied. 23.2.1. The vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratios are not greater than the values obtained as below. Number 1, basic values of span to effective depth ratios for spans up to 10 meters. First, if you have span to depth effective depth ratio, now span again clear span, like if we clear span LC, this is clear span. To effective depth D, or you can also name it as DE, effective depth. This is DE is here, or just D. Now what is this given? For cantilever, इसमें आप for cantilever क्या लिखा है? 7. For semi supported, for continuous is the third one? 26. So what are these? These are the limits. Limit means maximum. So maximum is this. This is maximum that we are providing. What's the maximum here? When you have a cantilever, what is this? What does this tell you? Span to depth. Span to depth. A cantilever, you cannot have greater span. This tells you that. It has to be limited. For example, you have put now depth. For example, we started from the first thing. Width कितनी दी हमने? For example, 200 दी. 200 फिर हम depth कितनी लेंगे? 200 into say 1.5 or 2. So 1.5 of 200 is 300. Now depth is 300. Then what should be the span of the beam? This is 300 into 7. 2100. So you cannot have 2.1 meters से ज़्यादा आप cantilever beam नहीं डाल सकते हो as per this. Now if I have to provide, then what should I do? Should I increase the depth? I can increase to 400 because my width is 200. I can increase till 2 times B. तो कितना कर सकता हूँ? समझो इसको. 2 times B. 200 मेरी width है. Depth, effective depth कितनी होगी? 400. तो 400 ये हुआ. 400 into 7 है 2800. 2.8. लेकिन मेरा कमरा यहाँ पर 6 मीटर कैंटिलीवर. This is not when it's cantilever. You cannot go beyond 2.8 meter if you are taking that. Then what do I have to do? I have to first increase the width till say for example I will increase it to 300. फिर मेरी depth increase होगी 600 maximum. तो 600 into 7 3500 or 4200. So 4.2 meter. If you have to increase even beyond that, so you will increase it till 400 width. But normally we do not go for a wider beam then. मैंने वहाँ पर क्यों लिखा? So 250, 350 width. I did not write about it. If you provide greater than 350 mm beam width, you are actually then going for wastage of material. You then have to actually go for, rather than deep, wider beam, you have to provide multiple beams. You provide multiple beams such that supports भी कम हो रहा है. You provide a beam like this here, तो span कम हो रहा है. So you do not mostly go beyond 350 mm of the width. तो 3 स्टेज है. पहला आप ज्योमेट्री कैसे फिक्स कर रहे हो, उसमें पहले आप विड्थ फिक्स कर रहे हो. फिर उसके बाद डेप्थ फ्रॉम कन्वेंशन, विड्थ फ्रॉम कन्वेंशन, डेप्थ फ्रॉम कन्वेंशन, फॉलोइंग 1.5 to 2 times विड्थ का रूल. फिर तीसरा आप डिफ्लेक्शन चेक कर रहे हो. Now for simply supported you have a wide range up till 20. If it was 200 or 300 mm, then you are providing the depth. So this will be 300 into 20. So you can easily go till 6 meters in a simply supported for just 200 by 300 beam. 200 is the width and depth is this. So this is how we maintain control on deflection. Then you are actually finally also checking from जो उसमें 2 clauses है ना ऊपर, span by 250 and span by 350. If there is no partition or with partition, then span by 350. If it is 6 meter, so it's 6000 by 6000 mm by 250 is whatever you are getting. So you have 24 is the mm is the deflection, final deflection that you are getting here. In that case, for example, when it was 6 meter beam. So you have now you know from structural analysis के आप कैसे deflection measure करते हो. लेकिन जो आप वहाँ से deflection आपको beam की आएगी from structural analysis after analyzing it, that has to be less than 24 mm for this beam if it was 6 meter without partition in between. So this is the limit. So for every meter addition of, there will be increase actually here, but not proportional. उतना increase नहीं होगा. You are also maintaining at the same time ये आप 23.2.1 आप check कर रहे हो. So then this was about the geometry of the beam. Now, how do you fix the reinforcement? Second. The first thing here is minimum longitudinal reinforcement. What is the minimum longitudinal reinforcement that you provide? For that, you go to page number 46, page 26.5 clause at the bottom of it. Requirements of reinforcement for structural members. तो उसमें beams दिया है पहले. 26.5.1 beams क्या mentioned है? Tension reinforcement. Minimum reinforcement उसमें दिया हुआ है. The minimum area of the tension reinforcement shall not be less than that given by the following. Next page पे आता है. Given by the following. AS by BD is equal to 0.85 by Fy. So this is actually AS minimum by BD is equal to 0.85. Now you are always allowed to take the code with you in the examinations, so you don't have to remember any equations. AS by BD is equal to 0.85 by Fy. What is AS minimum? It is the minimum steel area. AS minimum is minimum steel area. B is width of section or beam. B is effective depth of beam. Fy is yield strength of steel reinforcement. First of all, why is there a limit on minimum steel area? Minimum दिया हुआ है कोड में, there is, you have to provide minimum this much. You have to provide this much of the steel in tension. This is minimum steel area in tension or compression, both. In tension and compression. Whether you are providing compression steel at the top or you are providing tension steel, tension longitudinal steel, जो भी आप provide कर रहे हो, minimum has to be this much. Now, but your steel will not be dependent on only on minimum. This is just a minimum. It will be dependent on load कितना आ रहा है. So the amount of tensional moments that are generated at the bottom of this beam will decide the reinforcement amount. But if that comes, जो आप movement से calculate करके steel निकालोगे, जो हम करेंगे, वो अगर इससे कम आया, then you still have to provide at least this much. Minimum you have to provide this much. So this has been determined by the code. Now this is based on research. What do you get here? AS minimum is 0.85 BD by Fy actually. Now AS by BD क्या है? Area of steel by BD क्या है? This is telling you the percentage of steel. AS by BD. B into D क्या है? Area of the section. The effective area of the section. Capital D नहीं है, small d है. Effective area of the section. Leaving apart the cover. Cover को it's not in the picture. तो ये दे रहा है, इसमें effective steel इस envelope में कितना effective steel area. So this, if you multiply it by 100, then you will get the percentage of this. You will get the percentage of steel. Now it's actually telling you the minimum percentage. So you can also write it as PT minimum, where P is percentage of steel. PS minimum, not PT. Same designation. Will be equal to 0.85 into 100 by Fo, where PS is minimum is AS minimum by BD into 100. So you can also write it in this form. अब ये कहाँ से आया? I told you this has come from research that the minimum area has to be provided this much. Why? For two reasons. Number one, even if you require less than this in the tension, you are also requiring reinforcement for shear purposes. You will come to know that once we study shear, there are three things for shear. One is, I'll briefly discuss it. Shear is provided by one, by concrete itself. Shear resistance is provided by. Shear resistance to shear forces is provided by concrete itself. Second, by longitudinal reinforcement. Third, by shear stirrups, जिसको हम stirrups कहते हैं, rings. But the major component is taken by stirrups. In case of slab, ये भी मैं यहीं पर कहता हूँ, by bent up bars, and in some cases you also have double bars which provide the shear. आपने स्लैब में देखा होगा कि एंड में हम ऐसे बेंड करते हैं लोहे, ऐसे लेते हैं फिर एंड में बेंड करते हैं.